Okay, welcome back. In today's lesson, I want to take a bunch of seemingly unrelated topics and string them together because they are related. Essentially, what we're talking about today is the climate and how that influences your field of horticulture, be it landscaping or whatever you're doing, parks management, or if you're growing poinsettias. Climate plays an important role in all aspects, be it plant development or insect development. And of course, starting off with the first concept, something called growing degree days. What this is all about is insects and trying to understand or anticipate when insects will become a problem. And insects, unlike us, are cold-blooded, right? That means that their their body will equilibrate with the same temperature as their climate. So when it's cold outside, their body's really cold. When it's warm, their body's really hot. And in biology, all the chemistry that makes us alive, those processes are their speed is temperature dependent. So in colder conditions, insects will just grow and develop more slowly, and in warmer conditions they'll develop more quickly. So um, we try to tap into that by tracking something called growing degree days. um, we'll touch on phenology afterwards, which is also related to climate and temperature, but on a sort of on a broader level. But with growing degree days, unlike using a calendar where you say, okay, on this and this day, that particular pest will emerge from the ground every year, and we will just spray every year at that time. The trouble is with that kind of strategy is that it's imprecise. And we know from climate debates that, obviously seasons fluctuate wildly. You can have an early spring, a late spring, a hot summer, a cold summer, a wet summer, a dry summer. There's a lot of variability. And that variability contributes to unevenness when insects are to emerge. So again, thinking back to what I said before, that an insect's growth and development is temperature related. So on a warm day, that insect's marching forward in development quickly, and then on a cool day, it slows down. So if you have a warm spring, that insect's going to develop more quickly and emerge sooner versus a cool spring. And again, if you have a fixed calendar date for anticipating a pest, you're in trouble. So things like temperature, like it says here, humidity, rain, they all play a role in developing an insect, right? And so we try to get around that by calculating this growing degree day. There's an important concept here. It says established basal temperature. Um, Most of the time it's 10 degrees Celsius. But what we do, now there's some math, but it's really not complicated. Don't worry about it. So what horticulturists will do is that once we get close to near the end of winter, right? So that means that in your particular climate, once the temperature is starting to be above freezing, we will begin to calculate daily temperatures. Because obviously, when the ground is frozen, the insect is not developing very minimally. Now they can be below the surface, but it's negligible. Things start to really pick up the pace when things are above 0 Celsius. So what we do is we take the highest temperature for the day and the lowest temperature for the day, add them together and divide by 2. So we get the average temperature for the day. And then we subtract the base temperature. So in this case, 10 degrees Celsius, right? So as an example, if your lowest temperature for the day was 10 degrees Celsius and your max was 20, and with a base temperature of 10, we end up with 5 growing degree days. Okay, so that means we keep adding that. So that would be for, say, Monday, March the 10th or March the 20th. And then for Tuesday, March the 21st, you do it again and you add it to the previous. And you'll see as on this graph, it starts to accumulate, right? You're adding the growing degree days one to the other. As you go, the number increases. So as the days march on, our accumulated growing degree day begins to build and build and build. And then we reach thresholds where insects might emerge. And these numbers are typically published on what we call agricultural extensions. So wherever you are in Canada and the United States, your province or your region will have an agricultural extension, which is a group of people that help farmers make educated decisions about how to grow their crops, and they keep them on track with new technologies and new techniques. And they also do you the favor of calculating growing degree days and letting you know when you're approaching key dates. So here on this table, you can see for March 25th, we have a growing degree day of 5. Let's say we decided that that's when winter's over. We're going to start calculating. By the way, if you get a day where the temperatures are below 0, you just put a 0 there. Obviously, it's going to add 0 to the total, so it's irrelevant. But let's say we continued each day. We had a growing degree day of 2, and then 7, and then 5. And over here, you can see they accumulate. And eventually, say by April 28th, we end up hitting a growing degree day total of 225. And then all of a sudden, you are at a point where, hey, there's specific insects that have now had enough warm days that they could be emerging from the ground. I need to go out and control that particular pest. The assumption here is that if you wait till a pest emerges and you see it in your crop, it's usually too late. And so to try to anticipate that problem helps solve far more problems. So again, a negative number counts as a 0 in your growing degree days, right? So as you're accumulating. Here's an example. This is for European corn borer, which is a devastating lepidopteran that goes after corn. And you can see here that they're totaling growing degree days starting January 1st. So it would have been like, 0 for most of that for a while. But anyways, after they've achieved 740 growing degree days, they get their first moth flight. And the moth is going to lay eggs at 850. So these are control points, right? You could say, is it make sense to control the moth stage? That could be tricky. Is it better to control the first larval stage? That's at this many growing degree days. The second stage, the third stage. Now, interesting, why they even bothered to identify the different stages is because a lot of times there's different insecticides are required for different larval stages of development. So farmers have to make decisions based on what instar their particular pest is at. Yeah, I know. Complicated, isn't it? Second generation, that means we have 2 generations in a growing season potentially. Now, it depends on where you are in North America. This happens to be for Kentucky, which is, maybe slightly longer growing season. They may actually have 2 cycles in a year. It depends on where you are in Ontario. But every insect has its growing degree chart. And on the extra content folder for this week's class, there's lots of charts you can look at to see what different types of pests and when they emerge and stuff like that. So here's a map showing total growing degree days. So right off the bat, you're going to see that, down here in balmy Niagara and in the bottom of southern Ontario, we have the most growing degree days, which makes sense. And once you get into northern Ontario, quite often there's just not enough warm days for a lot of insects to even be a problem. So they may not have an ideal soil and an ideal climate, but they might have fewer pest problems, which is, not a bad thing necessarily. Moving on to phenology. So that's growing degree days, where we sort of empirically try to anticipate insects. Phenology is a really interesting approach to anticipating insects. And this method dates back to like prehistoric times when humanity was rummaging around the planet, living off whatever we could find and living under trees. Oftentimes we were trying to anticipate when certain food supplies would become available. And we would observe our surrounding environment and we would see changes in the seasons. And we would understand that when those changes happened, they were clues for when something else would happen. And that could be when there was food ready or whatever. Um, for example, indigenous populations in Ontario would plant corn in a specific area, and then they would leave it, and they would know by the dropping of the certain leaves on trees that it was time to go back to where they planted the corn, and it would be ready for harvest, and then they would store it for the winter. So they were using phenology, which is the science of appearances. It doesn't mean that what you're observing is specifically biologically related. It means that it's coincidental. That's an important concept to remember. So both weather and all aspects of climate influence all sorts of things, and nature has a way of just sort of integrating that all. Whether it's when trees drop their leaves or whatever, it's related to rainfall and temperature and sunlight. So it's a kind of a self-correcting, intelligent way to track things. And practically speaking, in certain cases, insects can only be present, like it says in the slide, when certain foods are present. So using phenology, we can anticipate, okay, so when a food source is available, we know the insects will begin to emerge. So phenology is making sort of associations. I have a humorous comic I stole from Gary Larson here, which, is sort of like the extreme of weather phenology, right? Where a guy's knee swells and he says, "Oh, it's rain's coming." The other guy's like, "Yeah, it's got to be bad. My hand's swollen." And the last guy's like, "It's got to be a doozy. My head's going." So, anyways, um, so phenology, right? So where we recognize that everything has evolved on this planet together, they coexist in the same climates, and so they coincide uh, in time, in space, when they emerge. Some classic examples: monarchs. Uh, their migratory paths are synchronized with milkweed, which is an important part of their life cycle and diet. And then, if you want to look for a really interesting and disgusting association, there's cicadas and this fungus called Massospora, which you can see here. It slowly eats their abdomen, and it just all slowly falls off, and they drop their spores in the ground. The crazy thing is that this fungus is so specific to cicadas that it emerges at exactly the right time as a cicada, which is like a 3 to 17-year dormancy. So this thing has the same cycle. It's following the same climatological inputs so that it emerges at the same time, which is pretty bonkers. Um, but anyways, nature is, as always, fascinating, mind-boggling. There's even some old sayings that farmers might use, like "Don't plant your corn till the leaves on the oak are the size of a squirrel's ear." So that's, you're trying to plant your corn in the spring, and you're trying to think when's the best time. So planting corn, by the way, is you're looking at soil moisture and temperature are critical for when you plant the corn. If you get it too early and the soil is too cold or it's too wet, the corn may not develop and may just rot in place. Now, an oak tree will allow its leaves to start to open and expand based on the soil temperature and moisture availability. And so here we have a simple clue that's unrelated to corn, but it gives the farmer a really good sense of when's the right time to plant corn. Another really good one that landscapers like to use is forsythia, which is this sort of woody bush that has these beautiful yellow flowers around Easter time and a little bit after. But anyways, the idea is that these flowers bloom based on accumulated temperature and moisture levels in the soil and in the air. And that happens to match when crabgrass is emerging. And so landscapers will use that as a clue for when it's time to treat people's lawns to reduce the emergence or the incidence of crabgrass. Um, I personally don't really care. I think crabgrass is just fine. It's green in August, but whatever. Some people like a perfect lawn. Um, so yeah, for example, here at 13 degrees Celsius at 4 inches of depth is when crabgrass will begin to germinate. Crabgrass is an annual, by the way. It's not a perennial. So we're talking about germination. Those are the ideal conditions for it to germinate. Okay, so a key thing here, not necessarily connected events, but coincidental. They give us clues as to when things will emerge. This is just there's some links here on the PowerPoint, not in this video, but in the PowerPoint, you can take you to those websites. I just zoomed in on a section here. This is from the Utah State University, where they're publishing um, basically phenology charts for apple pests. And so you can see here at the top, they're looking at the developmental stage of the apple tree. So dormant, green tip, half-inch green, tight clusters, the flowers are pink but haven't opened, full bloom, etc. So when you are looking at your crop and you look at the development stages of your apple tree, you can anticipate the emergence of different pests. And so in this case, green apple aphids, right around here is the control time. Same thing for scale. Powdery mildew is right when the flowers are just pre-budding. Time to keep an eye on it, maybe spray preventatively. So it goes on and on. There's a very long list because apples are just brutal to grow and Mother Nature must not like us eating them. But anyway, so that's phenology. So keeping in mind that not every season is identical and plants and insects obviously have to adapt to that. One of the things that I thought this is kind of an interesting time to talk about it. I won't spend much time on it, but highlight that we have to adapt to. And I got a couple of slides because I still find that students don't necessarily understand what climate change is or whether it's even real. And we as horticulturalists have something unique to offer to people who have a hard time understanding it. Now, I've just talked to you about growing degree days and phenology and how plants take all the information about the climate. They take light levels, temperature, moisture levels, all that, and then they make decisions. So they're really almost a better indicator of climate than a thermometer. And one really fascinating piece of information that has been kept track of since like the year 812 is in Japan, they are obsessed with cherry blossoms and they track when the blossoms are at peak and they have for years. And what you're seeing here is how let me change my pen color, is how right around, the 1800s, the the time or the emergence of the blossoms has accelerated. So much so that Japan is thinking of changing its celebration time to match the day better because the cherry blossoms are opening so much sooner. And that's because we have climate change. It's a real thing. Um, what do you think happened in the 1800s? What would even have kickstarted this? The 1800s is when we had the Industrial Revolution. That's when the world was bonkers about melting iron ore and making steel and manufacturing steam engines and ships. And, then we went through a few wars and on and on and on. And this is March of 2021. Now, there's outliers all the way along. Absolutely, right? It's the nature of measuring peak blossom is that there's some subjectivity, but you can see that it's pretty tight and there's definitely something going on. This slide is from NASA. I think this is also a very powerful slide because what it's doing is the yellow is showing us um, how much sunlight is arriving on the Earth, which is giving us the solar energy, right? And so the assumption is that, okay, so solar radiation, this is watts per square meter. You see over here. If the assumption is that the light levels arriving at the planet haven't changed that much, then here is the temperature change relative to the light that's arriving. Now that's only 1 degree, but that's up to just before 2020. This data, I think it goes to 2012. So we are well on our way. Give me the liberty here to almost 2 degrees, from what I understand. So we are in a situation where we will have to adapt, just like plants and animals. Now, plants can autocorrect. They have that amazing skill to adapt to climate as it changes so they don't emerge at the wrong time. Um, so let's talk a little more about climate, but in the context of plant growth. Couple of terms for your exams and quizzes. The term climate is we're talking about the characteristics of a territory and the overarching characteristics. Not the day-to-day over short period like weather. We're talking about the characteristics of a region in the summer or in the winter. It tends to be fairly static. I mean, we just talked about climate change, but we're only talking about a couple of degrees there. But when we look at the temperature changes between summer and winter, we're talking big changes. So those are climatic characteristics that we're talking about. So climate refers to a region, and it's talking about temperature, moisture, wind, and sunlight. And that describes that particular geographical location. Now, there are very specific areas all over the planet. Obviously, we're looking at Canada here. And typically, our climate is influenced by two major things, the latitude and the altitude. Now, I've driven these hand rough arches, but this is latitude. So as you're moving towards the North Pole, you're moving up in latitude. And so obviously that's going to be colder. And then altitude, if we're in the Rocky Mountains, and then we come across the plains, and then Ontario, and then the Maritimes, altitude plays a role in terms of the temperature and the climate as well. So there are definitely regional differences. We'll talk about zonal maps later, but definitely. Then within the latitude and whatnot, there are also geological landmarks that make a difference. So proximity to a lake, a big body of water, it stores energy, and that helps warm a region as you move into winter and helps cool it in the spring. It sort of buffers changes. So right here in Niagara, we've got Lake Ontario, which right now the water's warm, so you'll see steam coming off it in the morning when it's cold. And that warm air comes across. I mean, it may not feel warm, but that lake makes enough of a difference that temperatures stay warmer longer near the lake than they would elsewhere, far from the lake. So a body of water helps a region be more moderate. So that's one of the reasons why in the Niagara Peninsula, because we have this warm lake and we have this escarpment, it traps air and keeps our plants from getting extremely cold conditions. Not always, but most of the time. And that allows us to grow things like fruits and wine varieties that need warmer conditions. A lot of our wine varieties are also varieties that grow in the south of France. So the Niagara area is definitely influenced by the escarpment. Um, there's a huge difference in farming above the escarpment versus below the escarpment. You won't see any peach trees or cherry trees above the escarpment. You'll only see them below the escarpment because that warm air from there's above the escarpment, then you hit the escarpment, and then we go here to the shore, and then it's Lake Ontario. Whoops, let me change colors. And it's Lake Ontario. And that buffering effect keeps this region warmer, and over here it's colder. So clean that up. So same thing with Lake Erie. It has a similar property, and funnily enough, Lake Erie also, because the prevailing winds, we get a lot of snow in Buffalo, which is a totally different climate. Like here we are, you might see a lot of snow in Buffalo and almost nothing in Niagara. That is localized because of things like the escarpment and the lake. So microclimates can occur on a regional level, and they can also occur in a microscopic level. This is just a map showing the Niagara escarpment, or the escarpment, as we're down around here, but it travels all the way to Lake Michigan, and it has a microclimate along its shoreline the entire way, or its exposed cliffs, I should say. So with a microclimate, talking about greenhouse students, for example, you can have a microclimate just by having plants close together. So here we have like planetary climate, regional climate, and then you have microclimates. Even within your garden, um, landscapers have to pay close attention to microclimates. A really good example of a microclimate in a garden is a south-facing wall. And the plants that you plant there are going to be impacted by that south-facing wall. The sun's going to hit it in the winter. They're going to be warmer sooner in the spring. They may get more sunlight. All sorts of factors that landscapers have to pay attention to for microclimates in a given customer's garden. Um, or if you're a horticulturalist working at a botanical garden, all the different gardens have their own microclimates. You can have a damp, low spot, a high, dry spot, a heavily shaded spot, a full sun spot, a windy spot, you name it, microclimates. So lastly, to help horticulturalists, there's this climatic zones map, which gives us a rating from 0 to 8, gives us an idea of where certain plants will thrive. You've probably seen this before on care tags or seed packets, where it gives a plant a zone rating or a hardiness rating, and that tells us where it's safe to plant it. There's lots of links in this week's class. Let me zoom in on this. Is the one from the federal government of Canada, um, showing southern Ontario, right? Here, we're located here, and you can see that there's quite a few differences between those territories. Let's zoom in a little bit. So if we look at where Niagara College is, which is somewhere around here, we are in the 7A zone. And up north, 30 minutes north of Toronto, so up around here, you're looking at a 5B. So the lower the number, the colder the climate. As you go further north, things get really cold. Hamilton seems to be largely a 6A. What's interesting is Toronto has gotten warmer over the years. I grew up in Toronto, so I know it well. It's currently what I call central Toronto or downtown core, is the same rating as where we are in Niagara. I'll give you a gardening example. Years ago, you couldn't get wisteria to grow in Toronto, and now it grows like a weed. Not a big fan of wisteria because it tore apart part of my garden one year. It's so massive. Be careful where you plant that. Put it in the middle of your yard, not near a wall or near any kind of structure. It's just going to tear it out slowly. It's like Little Shop of Horrors. Anyways, so hardiness zones, they are available. You click on that link. You can zoom into right where it is you're working and find out exactly what your zone is. In recent years, they were updated. They used to be a lot less granular. Now they're much more specific to not only include weather, but topography. So they actually account for the escarpment and things like that. One other thing to make note of is that the Ontario region, especially southern Ontario, the very bottom of Ontario is Pelee Island. It's very warm. It's on par with Northern California. So there's definitely some warm parts. So here's some quick review questions. A zone 7 is colder than a zone 5 or warmer than a zone 5 or receives more light. Well, it's warm. A body of water will normally make the zone milder or the zone colder. That's your climatic, your hardiness number we're talking about. So if a body of water is going to make it milder, it's going to give it a higher number, because if you're near Lake Ontario, that's going to help your plants survive. Should mention, gardening in Calgary is absolutely brutal, because Calgary is a city that fluctuates between +5 and -20 all winter, which means there's a freeze thaw cycle happening all the time. Not to mention their photoperiod is different, and you name it. Elevation. Probably a good thing I put this here, because I think I may have forgotten to mention that, but I did talk about the Rocky Mountains. So the higher up you go, does it make the zone milder or colder? So the higher your altitude, the colder the climate. So you're going to get a lower number. All right, let's move on to photoperiod in flowering plants. So again, this is related to climate because it's related to how the uh, the day length changes throughout the year. So why is it important? Well, because plants and some insects and animals and ourselves, but we're talking about plants here, they measure the length of day, and they need that in order to anticipate or detect seasonal changes. Um, Quite a few plants or flowering plants are definitely photoperiod influenced, right? So that means that as the day length changes, it triggers developmental changes, typically flowering. Um, and the reason being is that the plant is trying to match key pollinators. So when the insects are emerging, their flowers are ready to go because it's useless for the plant if it flowers at the wrong time because there's no pollinator nearby. So they're trying to target a specific pollinator. Um, they also want to make sure they don't flower, in the wrong season, for example. And they have to know that there's enough time for that once they initiate flower, that there's enough time left in the season that they can finish. It would be terrible if a plant started flowering in September and then, you know, hit first frost and got burnt before it had a chance to be pollinated. So obviously, photoperiod tells it, when, so that's intelligent about when it's going to flower. Let me explain a couple of concepts here because I've over the years discovered that students, I don't know, they just don't learn it in school or whatever. It's odd, but anyways, um, I often ask in class, why are the seasons different temperatures here in Canada? And a lot of times what people say is, well, it's colder in the winter because the earth is tilted away from the sun, so it's further. And in the summer, it's closer to the sun. That's actually incorrect because the size of earth relative to the distance from the sun is like a pinhead on the other end of a football field. And if you rotate that pinhead, its distance relative to the other end of the football is absolutely minuscule. But the difference on the angle has a huge impact on the intensity of the sun. And when you look at this picture, hopefully I am able to convey this. Um, in the summer, this is a beam. This is a beam of sunlight. These are the same width. The same amount of energy is in this beam, right? And in the summer, when we're tilted towards the sun, that beam hits the earth and it's spread over a smaller area, right? And in the winter, when we're tilted away, in this case it'd be on this side, the beam is spread over a much bigger area and the energy is spread out, which means there's less energy per every given unit of area, which means it's colder. Hotter in the summer where it's intense, colder in the winter where the light is spread out. Couple that with the fact that the day length is also shorter, means not only is the angle of the sun bringing less energy, but the day length is different. So it just things go, temperatures change wildly because of that tilt. And that's the reason. To help you understand the angle thing, think of a flashlight. If you shine a flashlight straight at the wall, you get a really bright spot. But if you tilt your flashlight and shoot it along the wall, you get a large, dimly lit area. And that's the difference between sun in the summer and sun in the winter. As far as the day length, sometimes this is also confusing. So in the summer, right, we're tilted towards the sun. We are rotating through the sunlight for a longer period of time, and our nights are short. And in the winter, we're rotating through the sun in a shorter period of time, and our nights are long. So that tilt that the Earth has a profound impact on our lives. Um, and I'm going to argue brings some good things like some variability. But there's times when I think a palm tree, a mojito, and a beach every day sounds perfect. But I'm not quite there. I'm close, but I'm not quite there. Um, this is a day length by latitude chart. This is kind of interesting. Um, the closer you get to the equator, obviously the day length changes less. So the further you go north to higher latitudes, the more the day length changes throughout the year. And I'm going to tell you that most plants that are photoperiod sensitive have evolved in more polar and southern and northern regions where there's more change in the day length. So whereas plants that have evolved in near the equator, they tend to use things like rainy and dry seasons to tell them when things have changed for when they're going to grow. So tropical countries typically have wet seasons and dry seasons. Their temperatures change a little bit, but not as much. Whereas we have a wild both photoperiod and temperature change. So how do plants measure photoperiod? I'm not going to get into the biochemistry, but I will mention that there are two types of flowering plants. And not all plants are photoperiodic, or what we say demonstrate photoperiodism. But anyways, ultimately we have what are called short day plants and long day plants. And it's important that you remember this is where things get confusing. I don't want you to get confused on your exam or in life in general. Um, it's a bit dumb that horticulture has chosen to label plants as short day plants and long day plants because the reality is plants actually measure the night, not the day. Yeah, that's right. They measure the night. They measure the length of the night, which means if it's a short day plant, it's expecting a long night. And if it's a long day plant, it's expecting a short night. That's an important thing. So when you see a question on the exam that says, you know, a short day plant requires what to flower? And then you're going to say it's going to be a long night. That's probably not going to get a question quite like that, but it's what came to mind in the instant. But anyways, so what typically we're talking about, so a short day plant means that it needs long nights or a short day, but a long night in order for it to flower. We're always talking about conditions for flower when we make these statements, where a long day plant is looking for a short night in order to flower. So let's look at this chart down here. Vegetative means the plant has no inclinations toward flowering. So obviously we have flowering and we have vegetative. So in this situation, we have a critical night length. Not all plants have the same critical night length. Probably depends on where they evolved relative to the equator. But anyways, so let's say for a plant that requires a short night, which would be a long day plant, in this case, it's flowering, correct. And if we have a long night, it's going to be vegetative. Like we're trying to stick to this side of the chart here. Okay? So the question would be where things get interesting for greenhouse people is okay, let's say you have a long day plant in the middle of the winter and you want it to flower. Well, what is a long day plant looking for? It's looking for a short night. And so what we do to trick the plants is we turn a light on in the middle of the night, right here. Now here we have a long night in December, and here we have a long night in December, but we broke it up with some light in the middle. And what happens is plants are, I mean, they're smart, but they're not that smart. Okay, let's be honest. Um, and they have a memory that's worse than mine, which means that they're starting to count the night, and then whoop, the light comes on, and like, oh, well, night's over, and then oh, night's back. But hey, it's a short night because we're back into the daytime now. So as far as the plant's concerned, when you have night interruption, as we call it, the plant is tricked into thinking it's a short night, and you get flowering. Okay? So I got another slide here to demonstrate this. There's a link on where I got this from on your PowerPoint slides with some pretty good explanations. So um, we have short day plants, and we have long day plants. And I'm going to ask you, what is a short day plant expecting? It's expecting a long night. So a really good example here is mums, chrysanthemums. They are a short day plant. Just think of fall mums. We grow them in the fall because our days are getting shorter, which means they'll flower. So as the day as the night gets longer, here the day is short, the night is long, chrysanthemums will flower. And if you put night interruption on, they would not flower. So we can manipulate that. And cut mum growers actually do that. They put night interruption on, and the mum just keeps getting taller and taller and taller and taller. And then when it's tall enough, they turn off the night interruption, and all of a sudden they get a flower. They get a beautiful mum. That's not a beautiful mum, but you get the idea. So they can control the height before they flower using night interruption. On this side, the echinacea is a long day plant, which means it's looking for a short night. So it flowers in the summer, no problem. And in the winter, if you want it to flower for some crazy reason, you turn on night interruption and it flowers because it thinks it's a short night. Because remember, plants have a short memory and they just remember whatever the last sequence was. All right, so hopefully that makes sense. Two other terms that are important when we talk about photoperiodism with plants is the term facultative and obligate. Fancy terms, but you should know them because then people will be impressed. Facultative means that having a photoperiod that's appropriate for flowering, it helps. It's not essential, but it helps. A good example actually is poinsettias, because poinsettias, which we know flower at Christmas time, are a short day plant, but they actually are more, believe it or not, they're more temperature sensitive than photoperiodic sensitive. They both work really well together. So what we say is it's facultative, where photoperiod that is absolutely essential is obligate. Just think of the term you're obligated. You have no other choice. You are obligated to pay your tuition. But the term facultative means it helps, but it's not essential. One last time to remind you that when you look at photoperiod, when it says short day, flip it to tell you that it needs a long night for flowering. Okay?